Hi all, welcome to Heights to Fly. Today we are discussing a topic relations and functions. First we are discussing about relations. Let's go through the basics of relations. What is a relation? Consider two non-empty sets. Two non-empty sets. Then every subset of A cross B defines a relation from A to B. Then every subset of A cross B defines a relation from A to B. Consider two non-empty sets A and B. Consider two non-empty sets A and B. Then every subset of A cross B defines a relation from A to B. For example, consider A is equal to 1, 2, 5, 7 and the set B is equal to A, C, M, N. Okay. We can define a relation like A cross B is equal to 1C, 2N, 5A, 7A, like that. Here we can define the elements of set A as domain and this as codomain. Here the elements included in A cross B relation A cross B is from B, C, M and A. This term is known as, this set is known as range. It is domain, codomain. The set, initial set is domain, codomain, and this one C and A. This is called range. A relation can be represented with an alphabet A. Consider the notation R subset or equal to A cross B, A comma B element of R. These are some notation. These are the basics of relations. A related to B. Then we can write it as A comma B element of R. This is subset of A cross B. This is element of. Next, type of relations. For our topic, types of relations are more important. The topic relations and the basics are discussed in the previous classes or previous year. Types of relations are the first topic. We can define types of relations into empty relations. One type of relation is empty relations. We can say that a relation is an empty relation if no element of A is related to any element of A. Once again, if no element of A is related to any element of A. Consider the set A is equal to set 1, 2, 3, 4. We are considering the relation R is equal to set A comma B where A minus B is equal to 10. A minus B, that is the first term, subtraction of first term and second term is the difference of first term and second term is 10. And we are taking A cross B, A cross A itself, here the set is equal to a null set or empty set which is a subset of A cross A. That means A minus B, 1 minus 1 is not is equal to 10. Any other values in the set A satisfies the condition A minus B is equal to 10. So we can say that the relation R is equal to 5. Hope you understand. Next is universal relation. Universal relation a set is said to be, or a relation is said to be a universal relation if each element of A is related to every element of A. If each element of A is related to every element of A. For example, R is equal to A cross A. R is equal to A cross A is an example. Every element of A is related to other element of set A. Another term is trivial relation. Trivial, it's a term. Trivial relations. Trivial relations. What is trivial relations? Both empty relation and universal relations are both empty relations and universal relations are sometimes called trivial relations. Both empty relations and universal relations are called trivial relations. Okay. Next, go to another type of relation, which is equivalence relation. Equivalence relation. One of the important topic. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. Once again, a relation R in a set A is said to be equivalence relation if R is reflexive, symmetric, transitive. Okay. What is reflexive? Let's discuss what is reflexive relation. Reflexive. A relation is said to be reflexive if A comma A element of R for every A element of A. Once again, if A comma A element of R for every A element of A. That is 1, 1. Example, as example 1, 1. If the set contains elements 1, 2, the relation should contain sets 1, 1 and 2, 2. This is the condition. A comma A, 1, 1, 2, 2. Next term is symmetric. What is symmetric? If A1 comma A2 element of R implies that A2 comma A1 also element of R for all A1 comma A2 element of A. Once again, if A1 comma A2 element of R implies that A2 comma A1 element of R for all A1 comma A2 element of A. That is, if 1, 2 is element of relation R, then 2, 1 should also become element of R. Next point is transitive. The definition is if a1 comma a2 element of R and a2 comma a3 element of R implies that a1 comma a3 element of R for all a1 comma a2 comma a3 element of A. Once again, if a1 comma a2 element of R and a2 comma a3 element of R, which implies that a1 comma a3 element of R for all a1 a2 a3 element of A. Consider as an example set 1 2 3, and the relation defined is 1 comma 1, 2 comma 2, 3 comma 3, then 1 comma 2, 2 comma 3. Here the relation is considering 1 1, 2 2, 2 3. All the elements have satisfying the condition A comma A. Hence the relation is reflexive. But for symmetric, 1 comma 2 is present, but there is no 2 comma 1, hence it is not symmetric. Similarly, 1 comma 2 and 2 comma 3 are present, but 1 comma 3 is not present, hence it is not transitive. In the example, in the relation A comma A is or 1 comma 1, 2 comma 2, 3 comma 3 is present, hence the relation is reflexive, but it is not symmetric and not transitive since these two conditions are not satisfied. Let's go to another example. Consider a question. Let L be the set of all lines. L be the set of all lines and R be a relation. R be a relation in L defined as R is equal to L1 comma L2 where L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. And to show R is symmetric but not reflexive and transitive. Let's draw the figure. Consider this as L1 and this as L2. According to the relation, R is equal to L1 comma L2. R implies L1 comma L2 where L1 is perpendicular to L2. We are checking the reflexive statement L1 comma L1 which is a false statement. L1 cannot be perpendicular to L1 itself. L1 cannot be perpendicular to L1 itself. Hence the relation is not reflexive. Next is symmetric. According to the relation L1 comma L2, we have to prove to be symmetric L2 comma L1 also. That means L1 is perpendicular to L2, L2 is perpendicular to L1. From this figure it is clear that L2 is perpendicular to L1 and L1 is also perpendicular to L2. L2 is perpendicular to L1 and L1 is perpendicular to L2 also. Hence we can say that the relation is symmetric. Both these lines are perpendicular, mutually perpendicular. And the last case is transitive. L1 comma L2, we are reconstructing L3. L1 comma, we know that L1 comma L2 and L2 comma L3. And this figure L1 is perpendicular to L2 and L2 is perpendicular to L3. But it cannot implies that L1 is perpendicular to L3. Cannot implies that L1 is perpendicular to L3. Hence it is not transitive. It is not transitive. Okay. It is proved that R is symmetric but neither reflexive or transitive. Next question. Show that the relation R in the set of integers. Show that the relation R in the set Z of integer, where Z integers, set of integers given by R is equal to set A comma B 2 divides A minus B. 2 divides A minus B. Once again the question, show that the relation R in the set Z of integers given by R is equal to set AB where 2 divides A minus B is an equivalence relation. To prove a relation is an equivalence relation, we have to prove it is reflexive, symmetric and transitive. First case, R is equal to, we have to rewrite it as R is equal to A comma B 2 divides A minus B. This is our condition. First we have to prove reflexive or not. Reflexive. For reflexive, set AA. That means 2 divides A minus A. That is the condition. Since A minus A, it can be divided by 2 because the value is 0. 0 can be divided by 0, which is an element of integer itself. So we can say that the relation is reflexive. Second case, symmetric. A comma B element of R, then 2 divides, our condition is A minus B, 2 divides A minus B. Again, when considering B minus A, 2 divides B minus A, because A and B are elements of integers. What are integers? Integers are numbers which consist of integers. These are which consists of numbers positive, 0 and negative numbers -2, -3, 0, +1, +2, etc. So 2 divides B minus A also. So we can say that A comma B element of R comma B comma A element of R. Last case is transitive. A comma B element of R, B comma C element of R. Both A minus B and B minus C are divisible by 2. There is no doubt for that, because we can divide these two numbers. Then we can rewrite a minus c, because to prove transitive relation, if a comma b element of r, b comma c element of r, then we have to say a comma c. We have to consider a comma c. That means a minus c. We can rewrite a minus c in the form of a minus b plus b minus c, which will result into a minus c. That means when we add these two values, we get a minus c. These two values are divisible by 2. Previous statement we state that. Hence a minus c. Therefore a minus c is also divisible by 2. Also divisible by 2. Hence we can say that it is a transitive relation. Therefore R is an equivalence relation also. Why it is an equivalence relation? It satisfies all the conditions for reflexive, symmetric and a transitive. Okay. Next question is, next question we are going to. Next question. It is an example. Okay. Consider R be a relation. Another example, R be a relation, and the set A is equal to 1, 2, 3, 4, 5, 6, 7. R is equal to set A comma B, where both A and B are either odd or even. R be the relation defined in the set capital A, and the set is defined here by the relation is defined as A comma B, where both A and B are either odd or even. Show that R is an equivalence relation. R is an equivalence relation. Okay. We define R is equal to A comma B, where both A and B are either odd or even. Either odd or even. To prove reflexive, to check whether it is reflexive, consider set A comma A and A comma A. So according to the definition, A and A are either odd or even. A and A are either odd or even. Here the condition will be satisfied because either the number A and A will be either odd or even. Hence it is a reflexive relation. Next is symmetric. A comma B element of R, and similarly B comma A is also element of R, because A and B can either be odd or even. Hence it is a symmetric relation. Symmetric relation. And finally transitive. A comma B element of R, B comma A, B comma C element of R. A, B and C can take either odd or even. So we can say that A comma C element of R. We can say that A comma C is element of R, because A, B, C can take either odd or can take either odd or even values. Can take either odd or even values. Next, so today our topic is or. On next class we will go through more examples related to equivalence relation. That is the problems discussed in our exercises. So thank you for watching. Thank you for watching. Subscribe and share for new videos.